This conference will now be recorded.
I think the time has come.
We'll wait a couple of minutes for the participants to arrive because there are only 2 participants now. They'll be joining one by one.
I can see 5 number of participants.
Yeah, there's only 5, including me.
Increasing, I think.
Yeah, it will increase.
Good, yeah, it's increasing.
Yeah.
Dr. Pukan, there was a presentation from ISM. Has it been completed?
No, tomorrow it is.
Simulation?
Yeah, it is tomorrow. Rajiv Upadhyay sir, he will be presenting on reservoir simulation. Tomorrow at 3
Yeah,
p.m.
yeah. Okay, okay. I will. Well, if I get time, definitely I will attend that. He's
Yeah,
my batchmate.
batchmate.
So, yeah,
Rajiv sir
yeah.
is a
2003 batch. Yeah, yeah.
okay.
He's my batchmate from Indian School of Mines. We studied together. So after that, we
Okay.
moved around the world and then lastly landed in the Indian School of Mines.
Yeah, yeah. Okay, should we start? I'm starting the session. Okay. So, good morning, everybody. Good morning to the 4th day of this ATAL Academy sponsored faculty development program. It's sponsored, organized by the Department of Petroleum Technology, Dibrugarh University. So, I am so pleased to welcome our first resource person for today, Dr. Manish Kumar of Oil India Limited. He'll be speaking on a very important subject of upstream petroleum sector, that is the reservoir engineering. Dr. Manish Kumar is presently working as a chief reservoir engineer at Oil India Limited, National Oil Company of India. He did his BTech from the Department of Petroleum Engineering from IIT ISM Dhanbad in the year 2003 and PhD from the University of Petroleum and Energy Studies in the year 2019. He has published several research papers in national, international journals and conferences also. His research interests are enhanced oil recovery, field development planning, well testing, and reservoir simulation. Please join me in welcoming Dr. Manish Kumar. Over to you, Dr. Manish Kumar.
Yeah, thank you, Dr. Pukan. Indeed, a very nice initiative from Dibrugarh University, and you are doing a very noble job. So, friends and colleagues and seniors, so my name is Manish Kumar, as introduced by Dr. Pukan, and today I will be delivering glimpse of reservoir engineering because when we studied the subject was taught in 2 to 3 semesters, and I will try to give you some glimpse and try to generate some interest in you so that you can take it forward. And in case there are some issues which need to be dealt, we can deal
Yeah,
it
the connection is
offline or
lost.
online methods. Can you hear me? Hello? 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 Hello?
Oh, it's coming.
Dr. Pukan, can you listen me?
Yeah, I can hear. My connection was lost, so you can start now.
Okay, okay. So let me minimize the screen. Yeah, I think it is okay to go. So coming to the very first slide, that depicts the outline of the presentation. So initially, I will define reservoir engineering, and definitely reservoir engineering will come out of reservoir. So it is necessary to define what reservoir is. Next, the functions of reservoir engineering, and there are several aspects of reservoir engineering like volumetric analysis, drive mechanism, reserves, recovery. So I will be dealing in different slides, but the outline presented here will not be limited. There are so much things which we will be talking in the subsequent slides. So revising. So you must be knowing the name of the famous author Kraft. He defined reservoiring as the application of scientific principles to the drainage problems arising during the development and production of oil and gas reservoirs. So you can see three keywords that are repeating here. That is, first is oil and gas reservoir, and the second thing is development and production. So what reservoir engineering aids to, it tries to help in developing oil and gas reservoirs and applies basic principles of physics and mathematics. Now, how do we define a reservoir? So, for easiness of understanding, you can see a schematic diagram of a subsurface reservoir. So, from the top part, which is shaded in light gray, that is a cap rock. Cap rock is nothing but a rock which will not allow any fluid to pass through it. Means the ability of flow through the porous media is called a permeability, and this permeability value is very minimal. Just like if you know about the rocks, sandstone, shales, carbonate, so which is mainly composed of shales, so which will not allow the fluids to flow through it. And beneath the cap rock, you can see three different layers. The top layer will be of the gas, then oil, and lastly the water. Here, gravity pressure plays a major role here because the gravity of gas is the least and the water is the most. So, according to gravity, they will segregate beneath the subsurface. And to define a reservoir, there are some characteristics like there should be it should be porous. Porous is nothing but it should have some wide spaces between the grains so that some liquid like oil or gas can stay in it. It should be permeable, means fluid should pass through it, and there should be a trapping mechanism. So the trapping mechanism is nothing but the cap rope which is sealing it from the top. Now, what are the functions of the reservoir? So the very first function of reservoir engineering to determine how much hydrocarbon is there. And if I'm talking about hydrocarbon, it can be divided in two parts, oil and gas. So estimates of oil in place and gas in place that can be determined from using the reservoir engineering concepts and the identification of drive mechanisms. So in the previous slide, we have seen three different fluids like gas on the top, oil in the middle, and water in the bottom. So what is the energy contribution of gas cap, bottom water, and the oil zone itself by virtue of compaction drive or depletion drive? The third very important aspect, the estimation of recovery factor, means how much oil you can recover. Suppose you have got 1 million barrels of oil behind the subsurface. So how much oil you can recover? So roughly a recovery factor of 30 to 35% is there. That is the maximum, and the average recovery factor is around 25%. So you cannot take out more than that, and there are multiple methods by which you can use and try to take out more oil. And prediction of recovery as a function of time means forecasting. You have got a oil field and you want to tell what will be my production profile. Production profile is nothing but a curve which depicts oil, water, and gas over a function of time, how it will be there. According to that, you have to make your surface plans, surface facilities, all these things. So these four are the broad points of the which are functions of reservoir engineering. Now coming to the very first part, the volumetric analysis. Here you can see two things, the porosity and the current water saturation. As in the previous slide, I have already told about the porosity. It is the fluid storage capacity of a rock. And how do we determine it? It is the ratio of pore volume to the bulk volume. There are two terms, pore volume and the bulk volume. So pore volume is nothing but it is the interstitial space between the grains, and the bulk volume is the total volume. So if you take the volume of pore volume to bulk volume, the ratio will depict the porosity. It is depicted by fraction or sometimes by percentage. And there are two types: absolute porosity and effective porosity. There are some grains which are not connected to each other. Means connectivity is not there. Suppose you assume a reservoir, and in one part connectivity is poor, there very less connectivity is there. Even though it has got more space, so the effective porosity will be reduced because there is some cementation material between the interstitial space. And there is another type also for defining porosity, that is primary and secondary porosity. Primary and secondary porosity is nothing but during in situ formation, the whatever porosity has come, it is the primary porosity, and if you try to change by dissolving some material of the solution material, it is a secondary porosity. Secondary porosity is mostly evident in carbonate rocks, whereas primary porosity is in sandstones. Now coming to the second important parameter, that is the correct water saturation. So the correct water saturation is nothing but it's the water trapped in the pores of the rock during formation of the rock. So you can see on the bottom there is an image with black spaces. So there are some black colors there. It is nothing but your white spaces, and there are some blue linings that is attached to the grains. So these are connect waters basically. All the blue shades in the bottom image represent their connect water. So the chemistry of connect water can change in composition throughout the history of the rock, depending upon the mineralogy present in the rock, and if there is some external fluid which is injected. Now I want to concentrate you on the top image, which is showing you the upscale part. The middle part is showing a core sample, and it has been upscaled to three different levels: 5 scale, 7 scale, and 10x scale. So you can see very clearly how the grains are interconnected to each other and how there is a porous species formed. In the middle, the core sample is there. You cannot see all this, but if you magnify it, definitely you will be able to see all these spaces which is being depicted in the bottom image. Now the second most important parameter is the permeability. It is nothing but it is the ability of the fluid to pass through it. If there is enough porous space and these porous spaces are not connected, then the permeability will not be there. Like porosity, there are three different types of permeability: absolute permeability, effective, and relative permeability. So not going into the details, but I will give you some idea on how we can estimate these permeabilities. The very first method and the most reliable method is the core flood experiments. Like in the previous slide, I have shown you the image of the core in the middle. So you take a core, try to inject some fluid through it, and try to see how whether the fluid is flowing through it or not. I have explained it in a layman's language, but it is a much more complex, and my friends from industry know that it is a rigorous, complex job. So, but for ease of understanding, you can take a core sample and assume that some fluid is passing through it or not. So that will give you an understanding that this particular core is having permeability or not. The another estimation is porosity K5 transform. I have written an abbreviation for permeability, that is K and 5 porosity. So there is a transform also, like you have the colleagues from mathematical background must be knowing about the equations, the logarithmic equations, like y is equal to a into e to the power x, or y is equal to mx plus c, something like that. So this a relationship can be used, and we can estimate values of permeability using the porosity. And the well test interpretation, it will give you dynamic equivalent liquid permeability, which is very important in terms of it is measured in the in situ conditions. So this well test interpretation give you a holistic view of a drainage region of a particular reservoir. So it will from production point of view, the permeability determined from voltage interpretations are much more important. Now coming to the unit, so I have not taken the whole derivation of the Darcy's law. Darcy's law gives you Darcy's law is nothing but it is a equation for deriving permeability, and there are 2-3 terms like in the bottom you can see a equation depicting V, U, mu, L, and delta P. So these are velocity, viscosity, length, and the pressure differentials. So a person, anyone who is having some physics background, so can deduce this that the velocity is nothing but length by time. And if you try to go on this manner, you will deduce that the unit is L square, that is meter square or feet square. So this is the unit. So I think if anyone talks about this particular thing, you should be knowing where from permeability is coming from, which experiments, what is the unit, what it is, and what should be the scales. The scale part has been given in the bottom image, and you can see. If you, I am using a drawing tool and trying to depict this grable part. Try to see this grable part, and you can see that the range of permeability of it is going in the 10 to the power 5 darcies. Okay. So this is the highest permeability, and if you go to the Selly part, so this is in the range of 10 to the power minus 7 or 10 to the power minus 8. So it is very less. So just to give you glimpse, what can be the range of permeability. So this will give you an understanding what will be the range. And there is further subdivision of rocks and unconsolidated rocks deposits. There is by dictionary meaning also you can see a difference of consolidation and unconsolidation. But for ease of understanding, I will say that unconsolidation is nothing but the rock is not binding together. Means enough cementation material is not there between them. So it cannot be bound. It is a free flowing sand, something like that. You can understand. Likewise, I was talking about the estimation of permeability. So there is another very important parameter, so that is relative permeability. Okay. So relative permeability, why it is important? Relative permeability is because in the initial slide I have shown you an image of a reservoir where while water and gas are coexisting. So what do you think? Means if you drill a well, then only oil will be flowing, gas will be flowing, or water will be flowing. I from practical understanding and practical point of view also. this all the three phases will be flowing. Oil will be flowing, gas will be flowing, and water will be flowing. So the mobility of one phase is always more than the another phase. So the mobility of gas will be the highest, followed by oil and followed by water. So you can see a image on the right hand side, which is telling about the relative mobility on the y-axis and water saturation on the x-axis. And you can see two distinct curves. I will use the drawing tool and try to do something. So I am talking about this particular curve. This is a very flat curve, so lying between 0 to 0.2. So this is how this water is moving from the reservoir, and this is a typical representation of a water weight drop, where only oil is flowing and very less amount of water will be flowing on higher water saturations also. So this curve is representing water, and the another curve marked in green, it is representing oil. So with increase in water saturation, you can see how your oil curve is behaving. So I have there are different literatures. You can go through it, but for ease of understanding, you should understand that when there are two phases present inside the reservoir, one phase will also always try to prevail the other, and that's why the concept of relative probability has come. So I have shown you one example of oil water. Likewise, there will be a different relative probability will be there, that will be of oil and gas. So there will be two sets of relative probability: oil water and oil gas, and you have to use both the relative probabilities in any of the reservoir engineering calculations. Dr. Kukan, is it going all right? Means I'm audible and everything.
Perfect. It's perfect.
Okay, thank you. Now coming to the next very important parameter, PBT. So I will just read out what PBT is. It is the study of behavior of gas and liquid in petroleum reservoirs as a function of pressure, volume, temperature, and composition. So what it is trying to tell means how gas and oil will be behaving as a function of pressure, and let's talk about temperature only, because Earth is such as a huge body, so it is isothermal in nature. Means it is having constant temperature. Means it won't change. So I am leaving behind the temperature part, except for gas condensate reservoirs or reservoirs having uh, high API gas density. So I'm leaving that. So I will just concentrate on as a function of pressure how it will behave. So there are four different diagrams you can see. Likewise, there is a diagram on the top left is solution GOR versus pressure, then formation volume factor of oil, followed by formation volume factor of gas and viscosity. So one by one, I am coming to these parameters. So if you can see, I will try to demarcate the bubble point pressure, which is the inflection point. I will mark it this part. So on the x-axis, you can see in all the diagrams, you have got the pressure, right? And on the y-axis, there are different parameters. Means all these parameters are changing with pressure, and there is one inflection point which has been marked in the black colored pane. That is nothing but bubble point pressure. If I try to explain bubble point pressure in a very simplistic language, so my when I was during my college times, our professor Dr. S.N. Pandey give an example, and I will reiterate the same example to all of you. Uh, that time, cold drinks was a very uh, not accessible to everyone like 2 days, 20 years back. So I'm giving example. You take a straw, don't open the cap, and try to penetrate from the top, and you will see the bubbles will come out. So the pipe that you have drilled into the coke, that will act you as a tubing, and the bubble that will be coming out. So the pressure at which the first bubble comes out, that is the bubble point pressure, and it is very important in the reservoir engine. And all the inflections of different attributes like solution GOR, BO, viscosity, these are turning from the bubble point pressure itself. So you can see if you maintain a reservoir above bubble point pressure, your RS is good, your BO is also good, and viscosity is also on the lower side. So these are the favorable conditions for any productions. So just try to keep it in the mind the idea of bubble point pressure, and the reservoirs should be kept at all the conditions above bubble point pressure for maximum productivity. Because you can see if you are having lower viscosity, mobility will be more, and if your formation volume factor is of oil is more, means it is having more amount of gas in it, and it will help the liquid from subsurface coming from subsurface to the separator. So these are the. I'm not going into the details of it, but try to remember these 2 points: the bubble point pressure and how the reservoir should be kept, basically, and why it should be kept. And there are different methods, laboratory methods, for doing this experimentation and trying to take out these parameters. The very first one is the constant composition expansion, which gives you the estimation of bubble point pressure, and the differential liberation, which will give you all these four plots, and the separator test, which will give, this is nothing but a class experiment, which is used for combining the results obtained from your differential equation and separator test, and using it in further studies. Now, in the very first slide in the outlines, I have told you about the estimation of how much hydrocarbon is there. So hydrocarbon we can divide in two parts: the oil and gas. The gas was on the top, and oil was in the between, and followed by water on the bottom. So you can see two different equations uh, for calculation of original oil in place and original gas in place. Just forget about the constant 77458 and 43560. It is nothing but you are trying to take out in a particular units like stock tank barrels for oil and a standard cubic feet for gas. Just try to concentrate on the basic principle. So what do you think means this oil in place? This is some volume. This is estimation of some volume. So if you take how do you calculate the volume? The volume should be area into thickness. The first part, this A is area and H is thickness. So you will be getting a total volume. And if you multiply it by porosity, so it will give you the void space that is inside, and it is the total pore volume that is in the rock space. And if you remember, there was connect water saturation that was marked in blue in one of the images. So if you subtract this saturation, that connect water saturation, from 1, assuming that the total saturation value will be equal to 1. So 1 minus water saturation will be the hydrocarbon saturation or the white saturation. So these particular values on the top will give you the estimation of oil in place, and it has been divided by BO. So here comes the PVT in the picture. So you have taken some. This is the volume that will be there inside the reservoir. When you're taking it to the surface, this will be contracting because there is gas which is dissolved inside the oil, and this gas will come out as you take it to the separator. It will be coming out of the solution. So that's why this BO has been divided. And always try to remember the value of BO, that will always be greater than 1. It can never be less than 1. Just try to, this is the thumb rule, and you can also refer the image. So it will, the original while in place will always be divided by BO. And coming to gas in place calculation, so the AH5 and the top numerator part is the same as it is in the volume place, and only the denominator here BZ, means gas formation volume factor, has been used. But, because, and the BZ value is always less than 1. Means when the gas will be coming from subsurface to surface, then it will be expanding, and that's why it will, volume will be more. So try to remember the value of Vg, that will be less than 1, and that's why this gas in place will be more on the surface. Now I have replotted the same image of the reservoir, where gas is on the top while in the middle and water on the bottom. So as I have already depicted that there are some exerting forces, because water will exert its own pressure, gas will exert its own pressure. Uh, Dr. Fukan, I just need a 1 minute break.
Yeah,
Hello.
no problem.
Okay.
Yeah, please take.
Yeah, thank you, Dr. Fukan. Am I
Yeah,
audible? Okay.
yeah.
So, yeah, okay, thank you. So I have redrawn the same image for ease of convenience for everyone. The gas is on the top, while in the middle, and water is on the bottom. So gas will exert its own pressure on while, water will exert its own pressure on while, and overall this will help to take out more oil out of it. And on the middle, you can see one schematic of well is there. This is the schematic of well, where you can see the fluid is flowing, means oil is flowing through it. And the middle, this particular part, this is the tubing, and this is the packer, and this the small the color bubbles. This is the bubble. This is the coming from the solution gas. So, what would be the contribution in recovery factor? So, here a tabular representation has been made. Solution gas drive means all the energy that oil is having will contribute to around recovery factor of 20%. And the gas cap on the top will aid to a recovery factor of 30%. And the bottom water drive will contribute to a recovery factor of 35 to 40%. And sometimes we are having both gas and water present. So overall, if all these are present, we can expect a recovery factor of around 60%. So this is how we are trying to estimate a recovery factor in the presence of different fluid present inside the reservoir. And this recovery factor, or this the contribution of the different drives, has also been plotted in the bottom part. Here you can see few distinct colors, like the top part, this one, the pink color. This is the energy that is coming from the water influx. You can see the maximum contribution is from the water influx, and you can also corroborate that the maximum recovery factor is coming from the bottom water drive. So throughout the prediction, throughout the part, means the reservoir has started production from 93 until 2009. You can see the contribution from the bottom water drive. This particular part has been the most, followed by the color in the red. That is from the gas cap expansion. This particular part, and followed by the fluid expansion. This particular part, which is the least one. So just try to remember if reservoir is having bottom water drive, so it will be having more recovery factor, and if it is having gas cap, it will also contribute, but lesser than the bottom water drive. And on the right side, you can see a graphical representation of recovery factor, reservoir pressure divided by original pressure, and recovery efficiency. So this is another representation of what kind of reservoir you are having. So some calculations is required, and if you put your points on this curve, you can easily see which dominant reservoir, which recovery mechanism is affecting this particular reservoir. Now coming to the material balance equation. Material balance equation is nothing but it gives you some estimation, like you can estimate initial volume place, what is the water influx, and you can also predict future pressures and production under continued operation. So material balance equation is a technique, reservoir engineering technique by which you can estimate the above three parameters like volume place, water influx, and prediction of reservoir pressure and production. So there is a principle behind this material balance equation, that is, uh, if we have got a volume of 10 liters, and you are taking out 3 liters out of it, 7 liters should be remaining. So on this principle only, this material balance equation has been formulated by using equations from mathematics, and physics has also been used. So you can see the same principle of material balance equation has been iterated here also, and there is a complex drawing in the bottom right part, which I will try to explain you in detail. So I'm talking about this particular part. So you can see this particular, the volume removed. So this volume removed can be this particular part, this NP, WP, and GP. That is, NP is while that has come out, WP is water, and GP is gas. So this is the volume removed. Now what is the volume that is remaining? The remaining volume is the remaining vial, and I'm not talking about the injections. I will talk about the water first, remaining vial, and net water. So in these equations, one thing is has not been taken into picture, that is injection. So the initial volume is equal to volume remaining plus volume removed, but if there are some injection also, then it has also to be added, and that's what this gas injection and this water injection is coming to the into the picture. For the time being, don't concentrate on the rock expansion part. So that is a very significant part and doesn't contribute much. And try to concentrate on this volume that has been withdrawn, what is remaining, that is while that is remaining water, and the injection in the form of water and gas. So whatever you are taking out and whatever you are injecting, there should be a balance between it. And there is a long equation that is being derived for all types of reservoir, like oil reservoirs, gas reservoirs, reservoir with bottom water drive, reservoir with gas cap. So there is a detailed calculations, and not going into it, but try to understand the basic principle and what we can deduce from material balance equation. Now coming to the reserves definitions. So now that we have estimated oil in place, suppose we have got 1 million barrels of oil present inside the reservoir, and I was always trying to talk about the recovery factor. Means out of 1 million barrels, how much oil can be recovered on the surface? So roughly a figure is there to 30 to 35%. So you cannot recover more than 0.3 to 0.35 million barrels by conventional methods. So this 0.35 million barrels that is coming on the surface, that is reserves in a layman's language, but there are several dimensions to it. So if I try to quantify it, there are four dimensions which will tell whether a particular volume of oil can be called reserve or not. So it should be, there are four criteria that should be satisfied. The first one is it should be discovered, it is to be recoverable. Commercial. Commercial means there should be a market for it. Suppose there are there are several companies which have taken their projects outside India, like in Nigeria or some location which is geopolitically disturbed, and aid that is discovered also, that can be recovered also, but that is not commercial because that particular area is not developed. So it has, that has to have some market also. Then only it can be called reserve. And the fourth point is remaining based on specific development projects. To try to remember the first 3 points, it should be discovered, recoverable, and there has to be some market, means commercial attribute should be there. And how can we estimate reserve? So there are four different methods: volumetric method, material balance equations, decline curve, and reservoir simulation. So I'm not going into the detail, but the outcome of all these four will be this recovery factor. So you use any methods like volumetric, material balance, decline curve, or reservoir simulation. This recovery factor will be, the recovery factor will be deduced from all these four methods. And for your ease of understanding and some illustration, I have used a plot on the bottom right that is giving you a plot between rate and time. And you can see three distinct curves marked in green, red, and blue. The bottom curve is called the exponential curve, the middle one is the hyperbolic, and the top one is the harmonic. So how the reservoir is behaving depending upon the rate versus time, which is accessible to any of the operator. So they can plot their data and try to see how, on which curve it is sitting, on harmonic, hyperbolic, or exponential. So this will also give you an estimation. If you fit your curve on this particular curve, then you can extend it also for future, and from there you can determine how much volume can be reduced. So the volume, this decline curve analysis will tell you how much reserves is already there. For the reservoir simulation, I think my colleague Rajiv will be delivering you a separate lecture, reservoir simulations. He is an expert on that, so definitely will be benefiting. And I will suggest every one of you to please attend that lecture. Now coming to the stages of oil recovery, you can see four different barrels. Like the first barrel is having boiling place of 366 million metric standard of barrel, and there are three terms are written like primary recovery, secondary recovery, and tertiary recovery. So we have already talked about recovery factor, and I have told you that the average recovery factor lies around 25%, which is stated in point number 2 under primary recovery barrel. So if you use conventional methods and if you try to allow the reservoir to produce of its own, then it will give you around 90 million stock tank barrel out of 366. That comes out of around recovery factor of 25%. Now, if you deploy the secondary recovery technique, then this you can recover 155. You can see the difference. It is from 90 to 155. There is a difference of around 60 65 million stock tank barrels. That is the huge volume. And if you deploy this tertiary recovery, you can you can take out additional 90 million barrels, and that will be accounting to 235 billion metric stock tank barrels. So you can see there are three distinct recovery techniques. If you deploy all these three, you can reach a recovery factor of 64%, which is a very decent number. And as you are aware that MOPNG has already given us the mandate to reduce the import by 10%, and we are trying to increase the recovery factor. This is also one of the major components in reducing the import. Now I have told three terms: primary, secondary, and tertiary. I will be dealing in more detail. So primary recovery is nothing but it is the utilization of the natural energy of the reservoir to cause the hydrocarbon to flow into the reservoir. So, what is the natural energy? Natural energy is nothing but there is water below the oil column and gas on the top. So, if these two particular mechanism is available, then your reservoir, the chances of reservoir pressure going below the bubble point pressure is very less if it is active. But if it is not there, definitely the recovery factor will be hampered. So, in many conditions, the portion on the top, that is gas cap, and the portion on the bottom is not present. You are left with only oil cap, oil. So that will give you a recovery factor of around 20%. Additionally, you can supplement some energy to the wellbore also, like artificial lift. I have used three terms: gas GL, which is gas lift. Second is the sucker rod pump, and third is the electrical submersible pump. And the components of natural flow is solution gas drive, bottom water drive, gas cap drive, and edge water drive. Now there is an issue with the pressure basically. What do you think? If reservoir is 3,000 meters, like in kilometers I talk, 3 to 4 kilometers below the surface, how much pressure is required? So roughly, if you use a thumb rule, that is a zero point 0.1 kc per meter. So for a reservoir, which is having a target depth of 3,000 meters, if I multiply 3,000 by 0.1 kc per meter, it will be roughly around 300 kc. So if the reservoir pressure is below 300 kc with in due time, so the fluid won't be able to come from subsurface to surface, and that is a major challenge, declining pressure with time. So you have to supplement that energy because you have created some void space in the subsurface and you have to refill it. So for refilling it, you have to use some external fluids. So that I will be talking you in the next slides. But the major reason is the reservoir pressure decline with time, and we have to arrest it. Uh, you have created some void spaces in the reservoir by taking out oil, gas, and water. Now that void space needs to be supplemented by external fluid. So I will be playing 5 spot water flood project and try to demonstrate you how this injection of fluid helps in increasing the recovery factor or maintaining the voids inside the reservoir. We'll see if it works okay. From my computer, it is playing. If you can see a blue line, that is a yes, Dr. Pugan.
Yeah, it's playing in this side also. Yeah.
Okay, thank you. So you can see you have taken water from the natural water table, and from the pipeline, it is going into the water treatment plant, and finally from the center well, you can see it is coming down, and this is the oil marked in blue, and the oil is marked in black and water in blue. You can see how water has displaced oil, and the same oil is coming from the producer wells. Now again the same sequence is repeating. You can see two different lines. The blue line where from water is coming, and this black line, which is giving the depiction of flow of fluid, flow of crude oil. Again, the water is separated from the crude oil, and again the same process is repeated. And there is some pattern, so I'm not going to the details of the pattern, but just try to understand. But if you inject water into the reservoir, so it will sweep the oil out of it, and oil will come out, and it will also act as a pressure maintenance. Now that we have talked about the two barrels, the primary recovery and the secondary recovery. If you remember the figures correctly, from primary recovery it was 19 million stock and barrel. From secondary it is coming 155 million stock and barrel. So if you want to go further from 155 to 263 million metric stock and barrel, so you have to deploy the third technique, that is the tertiary recovery, and most often it is also called an EOR. EOR is nothing but it is the abbreviated form of enhanced oil recovery. So I won't read the definitions, but I will try to explain you what EOR is. EOR is, in my perception and understanding, if you try to inject some fluid inside the reservoir and change the behavior of interaction between oil and water, so this will tend to reduce some components like interfacial tension, residual well saturations. So you are trying to change the wettability or the interaction between the components like oil and gas and water. So if you are injecting some fluid, that fluid can be steam, that can be polymer, surfactant, or it can be gas also. So by injecting any external fluid, if you are trying to change the interaction between the interstitial fluids, that is oil, gas, and water, with rock, then it may lead to increase in the recovery factor. So now coming to why you are, I think this particular thing I already illustrated. You want more oil, you have to move from primary to secondary and then to tertiary. Even though this slide illustrates more details on why you are required. So the very first point is decreasing discovery trend. Nowadays, you can see that the big oil fields have not been discovered in country itself. In oil India itself, I don't remember a very big discovery beyond 2003 and something like that. That were the biggest discovery, and after that, small discoveries are there. So if you don't discover, you have to use your existing infrastructure and existing oil fields, and you have to increase the recovery factor. I think most of you are aware about the import part. So when I was studying in my college, at that time the import was around 70 to 75% way back in 2003. But right now the import has increased to a level of 82 to 83%. So you can see how your consumption is increasing, and we are producing very less. So we are producing around 30 to 35 million metric tons from all over India, and we are importing. That only contributes around 15 to 20%, not more than that. So rest 70 to 80% are being imported. So we are producing volumes which are insufficient to cater our own needs. Consumption is increasing. So even upstream, even upstream and downstream both are using this petroleum. All the plastic that you see, any product that is made of plastic, that is coming from the crude oil itself. So that is also increasing, and the number of vehicles is also increasing. So that is increasing the consumption of the crude oil. The exploration cost is has been increased. This particular fact can be illustrated by just that those EG oil has gone and we have to move to the deeper reservoirs. Like earlier, we were trying to look into the possibility of 2,000 to 3,000 meters. Now we have to go beyond 5,000, 6,000 meters. On in onshore and in offshore, we have to go into the deeper part. So whether you go deeper in onshore, on land, or whether you go in the sea, the depth is increasing, and that's why that the cost of exploring the new field will also increase. So, taking summing it all the above. So, if you try to avoid the exploration part, you have to deal with the production only. And we are we are trying to increase the recovery factor. It's from the recovery factor of 25% to 42%. So there is a gap of 17%, and if we maintain this 17% recovery factor by introducing various recovery mechanisms from primary to tertiary, we will be able to solve much of our problems. So now coming to the different UR methods. So broadly, UR has been categorized in miscible UR, thermal UR, and chemical UR. So there are some typical terms which are being used. So I will be dealing it in the subsequent slides. So before going to that, so let's talk on the one by one. What is miscible, thermal, and chemical UR? So I was talking about injection of external fluid in the reservoir. So if you use miscible UR technique, you are injecting gas. So gas can be carbon dioxide, hydrocarbon, or nitrogen. The most favorable gas for any UR is carbon dioxide, which has lower minimum miscibility pressure, and then hydrocarbon, and then nitrogen. The second one is thermal UR, where you are using the thermal methods. You can inject hot steam, air, or you can burn a part of reservoir also. And the third is chemical UR. In chemical UR, you will be required to inject polymer, alkali, or surfactant. Now there are different mechanisms. So I have tried to cater some UR mechanism in this slide, and I will illustrate why tertiary mechanism or UR is required and how it functions. So let's try to see on some of the important parameters. So if you can see the bottom, sorry, the top left image, and you can see the heading. This is the effect of mobility ratio. On the top image, if you can see, this is the injected water. This is the mark the color marked in blue is water, and this is oil. You can see this is there's some fingering, some image, something like finger has emerged. So this particular phenomena is called fingering. Means the reservoir is not homogeneous, or there are some permeable streaks through which the water is flowing very fast. Means in this particular channel the permeability is very high, and here this permeability is low. In this particular part permeability is low compared to this particular part. So it is not allowing all the while that is marked in gray to be displaced uniformly. Now what should we do? So we can mix some external agents like polymer in the water and try to inject. Now you can see there is a uniform movement, and you can take out more oil out of it. Now the shape of the water, you can see it is very uniform in nature, not like on the horizontal side. So the mobility ratio plays a very important role. Mobility ratio is nothing but this is the ratio of rotation to displaced fluid A by mu, permeability by viscosity, and you will not see no fingering and improved soup efficiency. So this is one part. You have controlled the mobility ratio and reduce the fingering and try to take out more oil out of it. The second important part is the interfacial tension. Interfacial tension, if I try to say in a simpler words, is nothing but a rock has got some mineralogy, and by virtue of that, it attaches water to its surface. So, in order that some less amount of water should be attached to the rock grains, this and the interaction of attached water to oil. So there is a term called interfacial tension. So if you reduce this interfacial tension, definitely you will be allow the movement of trapped oil inside the grains to move it easily. So you can see an image on the top that this trapped oil is reduced, this interfacial tension is reduced. Means if the fluid that is attached to the rock grains, if it is not, it is allowing the fluid to pass through the oil to pass through it by virtue of reduced interfacial tension, the more oil will be produced. And this particular mechanism is done by using surfactants. If you inject surfactants in the reservoir, the interaction between the fluid attached to the rock surface and the oil will be reduced, and this will intend reduce the interfacial tension also. And the bottom image it talks about the miscible gas, miscible EUR, where one important parameter is there, minimum miscibility pressure. So try to concentrate on this particular point. You can see percentage of recovery. Just try to see this as a recovery factor, and this as a pressure. This is a reservoir pressure. So your recovery factor will be increasing till a level. So you can see a recovery factor of around 90%. So that is achieved in the laboratory, but it cannot be achieved in the fields. It will be much more, but you can have an idea how it will behave. You can quantify something. So you can see recovery is around 95 to 100%, and beyond that it is not increasing. Means if you increase the pressure of the injected fluid to around 1350 psi, so then gas will be totally mixed with oil. It will allow the oil to swell, and after swelling, the viscosity will be reduced, and the oil will be flowing freely. So by virtue of this mechanism, more oil will be produced. But we have to know what will be the minimum miscibility pressure. So this particular point is the minimum miscibility pressure. So you have to pressurize your reservoir to this particular pressure, and if your reservoir pressure is somewhere here or somewhere here, even if you inject the same fluid, you will be having lesser recovery factor. Just see how much difference is there. Sorry, it is done incorrectly, but there is a loss of around 10%, and here you are losing around 20% recovery factor. So if your reservoir pressure has declined sufficiently low, then your recovery factor will also be good. So don't try to see the numbers 90%, 70%, but try to deduce the differences between that. So this particular mechanism will be useful in your visual gas UR. This will be in the chemical UR. This will also used in the chemical UR. Now some more details on the visual UR. There are some mechanisms like CO2 dissolves in the oil, like I've already told. It's well said, and it makes the oil thinner, less viscous, and there is one term also that is swag. You are injecting simultaneously water and gas. In that technique, you are using gas from the bottom set of perforation and water from the top set of perforations. And these methods are very well used in the industry. Now coming to the tertiary recovery method, and there is a video which will demonstrate on how this CO2 enhanced oil recovery works. We'll just play it. So now you can see a depiction of the reservoir, and you can see how much oil is recovered, and why this is CO2 can be used for extracting more amount of oil. CO2 has different advantages also. If you take out CO2 from atmosphere and inject it into the surface, it will you will also get carbon credits and reduce carbon footprints from the atmosphere. So now just a depiction of how it is working. Now this is the depth. You have come down to a level of around 19 to 2 kilometers. Now you have reached the level of around 3 kilometers, 2900 meters. These are different rigs. These are different rigs. These are sand grains, oils, and how this you can see how CO2 is interacting with oil, and this is making it lighter and trying to produce it. You can see there are two different wells. The red is marked by the CO2 injection well, and the oil extraction well is marked in blue. And this is a depiction of the offshore platform basically. So very good results have been seen by using CO2 EUR, and especially in USA, and they are claiming that this is one of the best techniques that have been very successful. Now that I have come to the end of the presentations, I think I should take questions because this was not an interacting session, and I had kept some time for interaction also. If Dr. Bukan allows.
Yeah,
Uh,
sure. So it was a very nice presentation, very systematic and also informative. Anyone has any query? You can type in the chat box or you can direct.
Yeah, because I have kept talking on from one side only. So please ask any kind of question.
Yeah.
I completely understand because I have already told in the very initial part that
Yeah.
this subject is a very big subject, and I will try to make it in a layman's language. But even then, whenever some talk is going on this subject, you can listen and you can understand us at least. So but don't hesitate to ask if you think it can be a very simple question. Please go ahead. You can
Good
clear
morning,
your
Manish sir.
doubts. I can. Yeah. Morning.
Good morning, Manish sir.
Good morning. Good
Sir, this is
morning. Please.
Sumit from Assam. Yeah, right now I am at Assam Energy Institute, a center of RGPT. Before I was at
Okay.
DUIT Dibrugarh University only. So we have met before. Sir, my question
Good.
is there any update, any miscibility or miscible flooding for CO2 in Bhopal, India? I heard before that some progress is going on, but I was not knowing exactly what is the status.
You are talking about some status update of some project, something like that, or
Yes,
because
sir. Yes, sir. Yes, sir.
on
Chemical you are kind
okay,
of, or miscible you are.
okay, even this is not of little bit out of context. I will answer in a very short. So uh, we have examined the concept of miscible CO2 EUR in laboratories and also tested in simulation. So we have got positive outcomes, and currently we are working with downstream companies because for any miscible you are taking to work, you have to have uh, CO2 because it is one of the base injectant fluids which will be working on a reduced minimum miscibility pressures. And if you cannot use hydrocarbons because it is sold, and the Prime Minister Narendra Modi's initiative is there to produce more gas, so we cannot inject the same gas into the formation. So we are only left with CO2 and nitrogen. Nitrogen is having very high MNP. So we are dependent on CO2 only. We are talking with several downstream companies, and very soon OIL will be going for visible UR technique in one of its wells.
Thank you, sir. Thank you.
There is a query from one participant. She's asking, sir, can you give a little more insight to porosity permeability transform? A little more
Okay, so
insight,
that is
porosity
yeah.
permeability transform.
Okay. Yeah, sure. I will give you that because this is a very good question, and any person who is doing simulation studies, so any person who wants to know if probability measurements are not there, I will just try to refer that slide, and then I will talk more. Yeah, K-pi transform. So why it is required? I think you have already understood. You don't have the four-flood experiments, and you don't have the voltage interpretation. So you don't have K value. Now that you don't have K and you require for any rejoining calculation, you require probability. So you can use the transform basically. Transform is nothing but uh, let's take an example of a straight line equation where y is equal to mx plus c. Okay, so x can be porosity and m and c you have to determine. I think geology plays a major role here. So if you are a person from geology background or aware of different formations, so in Assam Arakan Basin, there are different formations. Like if I take from the bottom, that is Lakadanthiria, that comes from the Eocene formation, followed by Oligocene, that is Barai formation, and then Tipam and Alluvium. But these are different major sand groups, and in the different major sand groups, there is already measurement. Suppose in Eocene formation, you have some measurement of K and phi both. So you can cross plot. So cross plot is nothing but plot by probability on the y-axis and positivity on the x-axis. Try to take a trend out of it from that particular formation, and you can and you have a different reservoir where you don't have this permitting measurement. So you can use this transform in the similar analog basically. So that will serve you some your purpose some reasonable uncertainty, but it won't be that much uncertain. So it has some logic or it has some analog. So where there you can use your transform where nothing is present and your analog data is available to you. I hope it answers your question.
Thank you, Dr. Manis. There is a small query from my side also. How is the fluid sampling done for? Yeah, how fluid sampling is done for collecting the fluids for PPT analysis?
Okay. Dr. Fuban, this is also a very good question, and I am exposed to this particular fact. So, likewise, what kind of sample do you require? Because sampling points can be at various points. It can be from the subsurface, it can be from the your wellhead, it can be from the gas line, it can be from the separator, it can be from stock tank. So there are multiple points from where you can collect the sample. These are the tapping points basically. And now comes the important aspect of time. When should you sample basically? And time is related with the pressure. So when the reservoir, when the first well is built, the sample should be collected. And as I already told you, there are different points. Your uncertainty will increase when you start going from the subsurface to the surface. Like uh, your uncertainty will be least when you collect your subsurface sample near the perforation, and then when you collect from the separator and then from the stock tank, because you will be losing some amount of gas that has come out from the vial. So this will, you can take from any point. There is no issue, but it is just that you collect your sample from the subsurface and when the first well is drilled. Let's say there now that you have come to the point that you have to collect the sample from the subsurface, there are 2-3 methods by which you can use. The very first method is the static sample. Static sample is nothing but you lower down by means of a baler. You can lower down your I cannot remember the name of the tool, but if you remember a cane or barrel, something like that, you will go with the help of a wire line, and the well is not flowing. You collect the sample and take it out and analyze it. The second one is the semi-static sample. You keep your sampler opposite to perforations, and then you open your choke. So this will allow you will give a pressure transient on the surface, so that will allow the fluid to flow from perforations after short interval. So the first fluid that is coming from the virgin formation, so that will give you the most accurate result. And the third method is your flowing sampling method. When the fuel is flowing, you lower the sampler and collect it. So I think these are the three methods, but you have to remember the fact that reservoir pressure should not be less than bubble point pressure. If a reservoir is saturated, then and you are trying to take out flowing sample from the subsurface, then you should be producing on a very low choke rate, so that your PWF, that is the bottom hole flowing pressure, should be greater than bubble point pressure. Otherwise, in a semi-static sample, it doesn't create that much problem. We prefer semi-static sample when the very first well is drilled, but sometimes the well is not allowed to shut, and we have to take samples from flowing wells also. But drawdown can be reduced, and you can use choke to create a back pressure for keeping the PWF above bubble point pressure.
Thank you.
Does it answer your question?
Yeah, sure. Thank you so much. There is another question, that this continuation of the porosity permeability transform. So she's asking, in Oil India Limited, which kind of transform is used? Do they use cross plot or other analytical transform that are available in the literature?
I think there is a lady asking this question, right?
Yeah, right, correct.
Okay. I think if she is asking this question, I think she must be aware about the. I have given a very simple transform of directive K and phi and using the analog, but I think she is aware of this rock quality index and flow to the indicators also. So if my question is on that line, so we are very well using that particular concept as the concept of rock quality index. So a reservoir with high porosity and permeability will be high rock quality index, and a reservoir with high porosity and low permeability will be on a low rock quality index. So there is a formula for calculating this RQI, that is 0.314 into square root k by 5. So this particular formula can be used uh, for clubbing your different. Suppose you have got 10 different samples and you want to club it. How we will be clubbing that? What are the samples that we will be using for averaging? So according to RQI, you can club it. And the flow zone indicator is another concept. So that is nothing but RQI by 5. 5 is effective porosity, 5 by 1 minus 5. So if I remember correctly. So RQI and FZI, these are the two different methods that can be used for clubbing and trying to reduce combining basically. And you can combine this high quality, you cannot combine this high rock quality index group with the low rock quality index group. That will be more appropriate. And it is also dealt with the phases. So one particular transform that you can use in the high rock quality index group, and the other one the medium and the low. So these my experience is I use 2-3 transform for the 3 different kinds of phases in the UI simulation work, and that's what is. I hope this answers your question.
Okay. Any other question? So it seems there is no other question. So I'll give the end remarks. So on behalf of everyone, I want to thank Dr. Manish Kumar for sharing his knowledge and expertise on the topic of reservoir engineering, which is a very crucial part of the upstream petroleum technology. I believe everyone enjoyed your presentation. So your lecture helped us to understand about reservoir engineering, the functions of reservoir engineering, the volumetric calculation of oil and gas by material balance, and also about the driving mechanisms, the reserves, different recovery processes, the EOR and their mechanisms. So it was a pleasure listening to you, Dr. Mandis. So once again from Dibrugad University, from everyone here, thank you very much. Thank you for coming and sharing your knowledge. Thank you.
Thank you, Dr. Pukan, for giving me this opportunity, and I wish uh, all the participants to learn and learn. There is no ending of learning. So even if you have got some queries or questions, so I have written my mail in the last part of the slide. You can mail me, or you can contact Dr. Pukan. So I'm always there. I'm also on the LinkedIn. You connect me to from that point also. We keep exchanging our knowledge, and from your intelligent questions, I've also learned that the crowd that is sitting here is well aware of and doing this particular subject. So it is further giving me that I should also be prepared very good for my next lecture. So I wish everyone all the best in the future. Thank you very much.
Thank you. Thank you so much.
Thank you.
So now we take a break of 30 minutes before we join the next session. So next session will be a lecture on well stimulation techniques by Dr. Rajat Jain of IIPE Vizag. So please join me again at 12:30. Thank you. Thank you so much.